Here's the truth nobody wants to say out loud. Most of what we buy our kids and call educational is just expensive plastic that ends up in a closet. But the right robotics kit, that's different. It's not a toy. It's a direct line into systems thinking, real debugging, and the kind of hands-on engineering that powers renewable energy grids, autonomous vehicles, and resilient infrastructure. My name is Chloe Miller, and I've spent years testing, breaking, and rebuilding these kits with real kids in real labs. You're listening to the STEM Lab podcast. Quick heads up before we dive in. Everything you're about to hear, all the research, all the data, all the script, is 100% human verified and written by real authors. But the voice delivering it to you, that's AI. We do it this way so we can get you high-quality STEM content fast and consistently without sacrificing accuracy or depth. All right, with that out of the way, if you've been listening for a while, seriously, thank you. It's incredible to know people are actually using this stuff in their labs and classrooms. And if you're brand new here, you picked a solid episode to start with. We drop new episodes every Monday, Wednesday, and Friday, so you've got a reliable rhythm of engineering breakdowns, project guides, and real-world STEM tools coming at you. Let's jump right in.
So, what exactly are educational robotics kits? They're integrated learning systems that combine mechanical hardware like motors, sensors, and structural components with programmable control boards, usually microcontrollers or single-board computers, and software environments ranging from visual block-based languages to text-based coding in Python or C++. The idea is simple. You teach engineering, coding, and systems integration through tangible projects. Unlike passive screen-based learning, robotics kits demand that you manipulate physical objects, troubleshoot mechanical failures, and watch code execute in the real world, where friction, gravity, and battery voltage actually matter. The best robotics kits for kids deliver progressive skill milestones. You start with pre-assembled bots running drag-and-drop programs, then advance to custom mechanical builds, sensor integration, and eventually text-based programming in languages like Python or C++. Quality kits are designed around expandability. You add modules, sensors, and third-party components as your child's understanding deepens. They're not one-and-done projects. Here's what separates a genuine learning tool from a novelty: compatibility with industry-standard platforms. Kits built on Arduino, Raspberry Pi, or other open-source architectures prepare kids for real engineering workflows. The Arduino Uno, for instance, is the same board used in university mechatronics labs and prototype workshops worldwide. When your child learns to program a robotics kit based on Arduino, they're not just playing, they're entering a community of millions of makers, accessing decades of open documentation, and building fluency with tools they'll encounter in actual STEM careers. Now let's talk about how these kits actually work. Robotics kits function as closed-loop systems. Sensors gather data from the environment, distance, light, color, touch. The control board processes that data according to programmed logic, and actuators like motors, LEDs, and servos respond. Your child writes the logic. The robot executes it. Feedback is immediate and visible. Starting with the mechanical layer, most kits begin with structural assembly. You're connecting beams, gears, wheels, and chassis components. Some use proprietary snap-fit parts. Think Lego Technic-style connectors. Others use screws and metal brackets. The mechanical layer teaches spatial reasoning, torque distribution, and gear ratios. You'll watch your child realize that wheel diameter affects speed, that motor placement changes center of gravity, and that structural rigidity matters when a robot needs to push or lift. Expandability starts here. Kits with standardized mounting holes, like the M3 and M4 threading common in VEX or MakeBlock systems, let you add custom 3D printed parts, salvaged components, or third-party sensors. If you're already running a home STEM lab with a 3D printer, you can design and fabricate custom brackets, sensor mounts, or gripper arms, turning the kit into a platform for open-ended engineering. Moving on to the electronics layer.
The control board is the brain, typically a microcontroller like Arduino, ESP32, or ARM Cortex, or a single-board computer like Raspberry Pi. Sensors are the senses. Ultrasonic distance sensors measure proximity. Line-following sensors detect surface contrast. Gyroscopes track orientation. Color sensors identify objects. Actuators are the muscles. DC motors drive wheels. Servo motors rotate arms or grippers. LEDs provide status feedback. Power requirements vary widely. Entry-level kits run on AA batteries or rechargeable NIMH packs, usually 4.5 to 6 volts. Advanced kits use lithium polymer or LiPo batteries, 7.4 to 11.1 volts, which deliver higher current for stronger motors but require safe charging practices. Store them in fireproof bags, never over-discharge, monitor cell balance. If your child is building competition-level bots or solar-powered autonomous vehicles, understanding power budgets becomes essential. I've burned through 3 LiPo packs, winning this the hard way. Then there's the software layer. Programming environments range from visual block-based languages like Scratch, Blockly, and MakeCode to text-based languages like Python, C++, and MicroPython. Block-based coding is ideal for ages 6 to 10. It teaches logic flow, conditionals, loops, and variables without syntax errors. Text-based coding, starting around age 11 and up, introduces real-world debugging, library management, and the kind of syntax fluency required for open-source contribution or industry work. The transition matters. Kits that support dual programming modes, blocks for beginners, text for advanced users, let your child progress without switching platforms. For example, Arduino IDE supports both visual programming via plugins and native C++, while Raspberry Pi-based kits run Python natively and support Scratch through extensions. If you're planning a progressive learning path, choose kits that grow with your child's fluency rather than capping out at one skill level. One more thing to consider: offline versus cloud-dependent. Some kits require constant internet access for programming, web-based IDEs, cloud compilation. Others install locally and function fully offline. If you value device independence or live in areas with unreliable connectivity, verify offline capability before purchase. So why do educational robotics kits matter for skill development? They teach systems thinking, the ability to see how mechanical, electrical, and software components interact and fail together. Your child learns that a robot doesn't work because of one brilliant line of code. It works because motor torque matches wheel load, because sensor placement avoids blind spots, because power distribution accounts for peak current draw. This is the mental model that separates hobbyists from engineers. They also teach iterative debugging, which is the daily reality of professional engineering. Code compiles, but the robot spins in circles. Is it a wiring issue, a logic error, a mechanical friction point? Your child will learn to isolate variables, test hypotheses, and document what works. That process, hypothesize, test, refine, is how we design better solar charge controllers, more efficient wind turbines, and resilient autonomous systems. It's the skill that matters most, and it's almost impossible to teach without physical feedback. Robotics kits prepare children for industry-standard tools. If your child masters Arduino programming, they can walk into a university engineering lab or a makerspace and contribute immediately. If they learn Python on a Raspberry Pi-based robot, they're using the same language that powers machine learning pipelines, climate modeling software, and renewable energy grid management. The tools aren't dumbed down, they're scaffolded, and that scaffolding is removable. Finally, robotics kits expose kids to the interdisciplinary nature of real engineering. You can't build a solar-powered autonomous rover without understanding photovoltaic efficiency, motor control algorithms, and mechanical load distribution. You'll find yourself linking robotics projects to renewable energy experiments, 3D printed custom parts, and even AI concepts if you add computer vision or machine learning modules. This is how you build engineers who see connections, not just specialists who know one tool. Let's break down the types of robotics kits and their learning paths. Not all robotics kits serve the same learning stage. Starting with block-based programming kits for ages 6 to 10, these kits use drag-and-drop coding interfaces like Scratch or Blockly and come with pre-assembled or snap-fit mechanical designs. The focus is on logic flow, sequencing, and sensor response loops. Examples include Lego Boost, MakeBlock MBot, Sphero Bolt. They're ideal for introducing computational thinking without syntax frustration, but they cap out quickly. Once your child masters conditionals and loops, they'll outgrow the platform. These kits work well as screen-free coding companions, bridging tactile logic games to visual programming. Next, Arduino-based kits for ages 10 to 16. Arduino kits expose kids to C++ programming, breadboard wiring, and modular sensor integration. They're the workhorse of educational robotics. The Elegoo Smart Robot Car Kit is a classic entry point. Check the link below to see the current price. It includes ultrasonic sensors, line-following modules, and IR remote control, all programmable via Arduino IDE. The learning curve is steeper. You'll encounter compilation errors, wiring mistakes, and library conflicts, but the payoff is massive. Your child gains fluency with tools used in university labs, prototype studios, and open-source hardware projects worldwide. Most Arduino kits run on 7 to 12-volt DC power from barrel jacks or battery packs, require USB connectivity for programming, and support Windows, Mac OS, and Linux. They're fully offline capable once the IDE is installed. Expandability is near infinite. You can add GPS modules, solar charge controllers, OLED displays, or servo arrays using standardized pin headers and I2C or SPI protocols. The downside? Arduino lacks native multitasking and advanced data handling. If your child wants to process camera feeds or run machine learning models, you'll need to step up to Raspberry Pi. Raspberry Pi-based kits for ages 12 and up. Raspberry Pi robots are full Linux computers on wheels. They run Python natively, support TensorFlow Lite for on-device AI, and handle multi-threading, networking, and multimedia. Kits like the SunFounder P-Car X include camera modules, servo-driven pan-tilt heads, and ultrasonic and IR sensors. Check the link below to see the current price. Your child can build object tracking robots, autonomous navigation systems, or even telepresence bots with real-time video streaming. Raspberry Pi kits require 5-volt, 3-amp USB-C power from wall adapters or power banks, micro SD cards for OS storage, 16 gigs minimum, class 10 speed, and Wi-Fi or Ethernet for SSH access or remote programming. They draw more current than Arduino systems. Expect 2 to 4 hours of runtime on a 10,000 milliamp-hour power bank. Raspberry Pi boards run Raspberry Pi OS, which is Debian-based Linux, which means your child learns command line navigation, package management, and system administration alongside robotics. The trade-off? Raspberry Pi boards are less forgiving with power interruptions. SD card corruption is common if you kill power abruptly, and they're more expensive than Arduino setups, but they open doors to AI and machine learning projects, computer vision, and IoT integration. Then there are competition-level kits for ages 12 to 18. Vex Robotics, First Tech Challenge, and LEGO Mindstorm's EV3 or Spike Prime kits are designed for team-based robotics competitions. They emphasize mechanical precision, sensor fusion, autonomous routines, and driver-controlled operation. These kits are modular, durable with metal components and industrial-grade motors, and expensive. Full VEX kits run around $500 to $1,000 or more. They're overkill unless your child is joining a robotics team or wants to compete, but they teach CAD-driven design, iterative testing, and the kind of pressure-tested engineering that mirrors real-world product development. Competition kits use proprietary control systems like the VEX V5 Brain or EV3 Brick with rechargeable battery packs, 2,000 to 3,000 milliamp-hour LiPo or NIMH, wireless programming via Bluetooth or USB, and support for Windows and Mac OS. They're not as open-ended as Arduino or Raspberry Pi, but they're optimized for reliability. Motors, sensors, and controllers are rated for hundreds of hours of continuous operation. Now let's talk about lab specs. What should you check before you buy? Starting with power requirements and runtime. Battery type matters. Disposable AA or AAA batteries are easy but wasteful. Rechargeable NIMH is sustainable with moderate current. LiPo offers high performance but requires safe handling. Voltage and current draw. Entry kits run on 4.5 to 6 volts with less than 1 amp draw. Advanced kits, multi-motor or Raspberry Pi based, need 7.4 to 12 volts and 2 to 4 amps peak current. Runtime, budget 1 to 2 hours for most kits on standard battery packs. High-draw systems like camera-equipped robots or multi-servo arms may run less than an hour. Consider secondary battery packs or USB power banks. Solar compatibility, some kits support external power input, perfect for integrating solar energy experiments and teaching energy budgeting in autonomous systems. Connectivity and programming interfaces. Wired versus wireless programming. Arduino kits typically require USB cables for code uploads. Raspberry Pi kits support SSH over Wi-Fi. Some advanced kits like Vex or Mindstorms use Bluetooth. OS compatibility. Verify Windows, Mac OS, and Linux support. Most Arduino and Raspberry Pi tools are cross-platform. Some proprietary kits like Lego or Vex have limited Linux support. Offline capability, Arduino IDE and Raspberry Pi Python environments run fully offline. Web-based IDEs like Code.org Robotics or some MakeBlock tools require internet. Expandability and third-party integration, standardized connectors like I2C, SPI, GPIO headers, or modular sensor ports let you add third-party components. Mounting compatibility, M3 or M4 threaded holes, or Lego-compatible studs enable custom mechanical designs. Software ecosystem, Arduino and Raspberry Pi have massive open-source libraries, tens of thousands. Proprietary systems have smaller ecosystems, but better documentation. Durability and repeated use. Snap-fit plastic kits like Lego or MakeBlock tolerate hundreds of assembly and disassembly cycles. Screw-together metal kits like Vex or some Arduino chassis are nearly indestructible but slower to reconfigure. 3D printed components, common in DIY-oriented kits, vary widely. PLA is rigid but brittle. PETG is more impact-resistant. If you're building a home STEM lab, prioritize kits with replaceable parts and open-source mechanical designs you can fabricate yourself. Let's talk about skill milestones and progressive learning paths. The best robotics kits for kids deliver concrete capability milestones, not just age ranges. Stage 1. Visual programming and sensor response, ages 6 to 10. Skills acquired, sequencing, loops, conditionals, cause and effect reasoning, typical projects, line-following robots, obstacle avoidance cars, light-seeking bots. Platforms, Scratch-based kits like Lego Boost or MBot, block-based Arduino plugins. Transition readiness, when your child can independently build multi-step programs with nested conditionals and debug sensor response issues, they're ready for text-based coding. Stage 2. Text-based programming and modular electronics, ages 10 to 14. Skills acquired, C++ or Python syntax, breadboard wiring, library management, serial debugging, typical projects, Bluetooth-controlled cars, ultrasonic mapping, servo-driven robotic arms, Arduino-based kits, MicroPython boards like ESP32 or Microbit. Transition readiness, when your child can write original functions, integrate multiple sensors, and troubleshoot wiring and code interactions, they're ready for Raspberry Pi or competition-level platforms. Stage 3. Embedded Linux, AI integration, and CAD-driven design, ages 12 to 18. Skills acquired, Python multi-threading, computer vision with OpenCV, machine learning with TensorFlow Lite, CAD modeling in Fusion 360, version control with Git, Typical projects: autonomous navigation with SLAM mapping, object recognition, solar-powered robots, competition builds. Platforms: Raspberry Pi kits, NVIDIA Jetson Nano for serious AI workloads, VEX or FIRST robotics competition systems. Your child is ready for university-level engineering coursework, open-source contributions, or prototype development internships. Now, subscription costs and consumable requirements. Most robotics kits are one-time purchases with no mandatory subscriptions. You buy the hardware, download free software like Arduino IDE, Raspberry Pi OS, or Python, and access open documentation. This is a major advantage over subscription-dependent STEM platforms. You own the tools, and your child's learning is ungated by monthly fees. Consumables are minimal, but they exist. Batteries. Rechargeable NIMH or LiPo packs eventually degrade. Budget $20 to $40 for replacement packs every 2 to 3 years. 3D printer filament if you're fabricating custom parts. PLA costs around $20 per kilogram. Replacement sensors or motors. Individual components range from $2 for ultrasonic sensors to $15 for servo motors. Breakage is rare with careful handling. Some premium kits like VEX or LEGO Mindstorms offer optional online curriculum subscriptions, $50 to $100 per year, but the kits function fully without them. You're paying for structured lesson plans, not core functionality. Let's talk about integrating robotics with other STEM disciplines. The best robotics kits for kids aren't isolated projects. They're platforms for interdisciplinary exploration. Robotics plus renewable energy. Mount solar panels on your robot chassis and program it to track sunlight or map shaded areas. Use a buck-boost converter to regulate solar input and measure efficiency under different weather conditions. This is how you teach energy budgeting in autonomous systems, the same challenge that governs Mars rovers and off-grid sensor networks. Robotics plus 3D printing. Design custom gripper arms, sensor mounts, or wheel hubs in Tinkercad or Fusion 360, then fabricate them on your home 3D printer. This teaches CAD to physical workflow, the same process used in mechanical engineering and product design. Robotics plus AI and machine learning. Add a camera module to a Raspberry Pi robot and train it to recognize objects using TensorFlow Lite. Start with simple image classification, identifying colored blocks, then progress to object tracking or gesture control. This is hands-on machine learning, no abstract datasets, no disconnected theory. Now, let's get into some frequently asked questions. What age should my child start with robotics kits? Your child can start with robotics kits as young as age 6 using block-based programming platforms like Lego Boost or MakeBlock MBot, which teach sequencing and sensor logic through visual drag-and-drop interfaces. By age 10 to 12, they're ready for Arduino-based kits with text-based programming in C++ or Python, and by age 12 to 14, they can tackle Raspberry Pi systems with AI integration, computer vision, and autonomous navigation. The key factor isn't age, it's progressive skill milestones. Start with pre-assembled bots and visual coding, advance to modular electronics and breadboard wiring, then move to embedded Linux and CAD-driven design. Do robotics kits require subscriptions or ongoing costs? Most robotics kits are one-time purchases with no mandatory subscriptions. You buy the hardware, download free software like Arduino IDE, Raspberry Pi OS, or Python, and access open-source documentation and tutorials forever. Consumable costs are minimal. Rechargeable batteries, NIMH or LiPo packs, last 2 to 3 years before needing replacement, $20 to $40, and individual sensors or motors, $2 to $15 each, can be replaced if damaged. Premium kits like VEX or LEGO Mindstorms offer optional curriculum subscriptions, $50 to $100 per year, for structured lesson plans, but the kits function fully without them. Can robotics kits work offline without constant internet access? Arduino-based kits and Raspberry Pi systems function completely offline once the programming environment, Arduino IDE, Python, Thonny, is installed. Your child can write, compile, and upload code without any internet connection. Some kits use web-based IDEs, like MakeBlock's MakeBlock Online Editor or Code.org robotics modules that require internet for programming, so verify offline capability before purchase if you value device independence. Competition-level kits like Vex or Lego Mindstorms program via desktop software that works offline, though firmware updates and some advanced features may require occasional connectivity. How do I choose between Arduino and Raspberry Pi robotics kits? Arduino kits, $50 to $150, are ideal for ages 10 to 14, learning electronics fundamentals, C++ programming, and sensor integration. They teach breadboard wiring, real-time control loops, and hardware debugging with simple, robust microcontrollers. Raspberry Pi kits, $80 to $200, suit ages 12 and up, ready for multitasking, computer vision, AI and machine learning, and Linux system administration. They're full computers that run Python natively and support advanced projects like object recognition or autonomous navigation. Choose Arduino if your child is new to electronics and text-based coding. Choose Raspberry Pi if they've mastered Arduino basics and want to explore AI, networking, or multimedia projects. Are robotics kits expandable and compatible with third-party components? The best robotics kits for kids use industry-standard platforms like Arduino, Raspberry Pi, or ESP32 with standardized connectors like I2C, SPI, and GPIO headers that support thousands of third-party sensors, motors, and modules. You can add GPS, OLED displays, accelerometers, or solar charge controllers using plug-and-play libraries. Kits with M3 or M4 threaded mounting holes or Lego-compatible studs let you integrate 3D printed custom parts, salvaged components, or competition-level hardware as your child's skills grow. Proprietary closed ecosystem kits, some Lego sets, entry-level make-block models, limit expansion to manufacturer-approved accessories, so prioritize open-source platforms if you're building a long-term progressive STEM learning path. Here's the thing. The best robotics kits for kids aren't endpoints. They're skill-building infrastructure. They teach your child to see technology as malleable, debuggable, and improvable. They turn abstract code into spinning wheels and flashing LEDs. They force iterative thinking because the robot doesn't care about your intentions. It cares about voltage, torque, and logic flow. When you invest in a quality robotics platform, when built on open-source tools, expandable hardware, and industry-standard languages, you're not just buying a project. You're giving your child fluency with the same tools used to design autonomous vehicles, optimize renewable energy grids, and build resilient infrastructure. You're teaching them that engineering isn't about following instructions. It's about iteration, failure, and the stubborn belief that the next version will work better. Start with a kit that matches your child's current skill level, but choose one that won't cap out in 6 months. Look for Arduino compatibility if they're ready for text-based coding, Raspberry Pi if they want AI and computer vision, or competition-level platforms if they're joining a robotics team. And remember, the best learning happens when the robot breaks, the code fails, and your child has to figure out why. That's not frustration, that's engineering. That's it for this episode of the STEM Lab podcast. Appreciate you spending your time here. There's a lot of noise out there, so it means something that you chose this. New episodes go live every Monday, Wednesday, and Friday, so you'll have fresh content waiting for you throughout the week. If you found this useful, do me a favor, leave a 5-star rating and write a quick review. It sounds small, but it's genuinely how other people find the show, especially folks looking for real engineering guidance, not just product hype. And go ahead and hit subscribe or follow so you get notified the second a new episode drops. Catch you next time.